All right, let's talk about charge density. So, charge density is very similar to mass density, which in the past we've probably just referred to as density, because in most classes, when we say density, we mean mass density, right? Whether it's, and typically it's going to be a volume mass density because, well, we live in a three-dimensional world. So, in fact, every object in our universe is three-dimensional. I mean, even a piece of paper has some width to it. So it is in three dimensions. So yeah, especially like in chemistry, we would definitely almost always talk about volume mass density. So how much mass there is per volume of a certain material. So charge density is pretty much the same thing, just with charge instead of mass. So go ahead and share my screen. There's three kinds of charge density that we're going to work with in this class. One of them is kind of like the equivalent to the volume mass density, this lower one here, uh, indicated by the Greek letter rho. This one's volume mass density. And so, or I'm sorry, volume charge density. So what that would mean is that would be how much charge there is per cubic meter of material. So you can see over here, the SI units for a volume charge density would be coulombs of charge per meter cubed. I'll go up to the top here. This is lambda, Greek letter lambda, and it indicates the linear charge density, which is, in other words, think of you have this perfectly thin line. I mean, you just have a line, right? And this line has charge on it, and there's a certain amount of charge per length. So that would be the linear charge density, units of coulombs per meter. And then this one here in the middle, that symbol is sigma, and it indicates surface or area charge density. So similar thing, let's say you have a flat sheet of something or some sort of two-dimensional manifold, and it has some sigma, and you want to figure out how much charge it has in a meter. Well, you could take that sigma and times it by a meter and figure out how much charge it has for that meter, or I'm sorry, for that square meter, right? Surface, square meter, coulombs per square meter. All right. So if the charge density is constant, then the total charge for each of these three examples, which is I'm going to indicate with big Q, for a linear charge density, you could find the total charge on the line or on the curve by taking lambda, the linear charge density, times the total length of the line or curve. And that'll give you the total charge. Unit-wise, right, lambda is coulombs per meter. Unit-wise total length is meters. And so the meters cancel, you end up with your coulombs. And down one below, we have big Q total charge equals the surface charge density times area, or surface area. So once again, the units work out nicely there. We have for sigma, it's coulombs per meter squared, and for total area, it would be meters squared. So once again, we cancel, get total charge. And so same thing for the last one here. We have the volume mass density times the volume gives us our total charge. Yeah, so if our charge density is constant, these equations work all across the board. If the charge density is variable or is a function of position, then calculus is likely required. And we really won't have to deal with a lot of that in this class. So I'm not going to worry about showing an example for variable charge density at this point. Over here, I have a few examples for a constant charge density. So here I have, I should probably write that down. Constant charge density. Both these examples are for constant charge density. So in this case, what we have is we have a circle of wire, and that wire has a constant linear charge density on it, and the circle has a radius r. So what we're looking to find is the total charge Q. And since we're looking at linear charge density, it's going to be lambda times the total length of the wire. And in this case, it's the arc length of an entire circle, which is the circumference. So in this case, we have lambda, the linear charge density, times the total length of the wire, which is going to be 2 pi r in this case. So if we had numbers here, we could go ahead and plug those in and figure out how many coulombs of charge total are on this circle of wire. And another example for surface or area charge density, what I have here is the surface of a hollow half sphere with radius r. And I'm wondering, if I have a constant surface charge density, then what's my total charge for the entire object? So we go up to the second equation right here. Q equals sigma times the total area, or total surface area. And in this case, we know that this is half of a hollow sphere. And we know that the surface area of a sphere is 4 pi r squared from a few videos ago. So we could, to get the half hollow sphere, we go ahead and just divide by 2. Total area here is 2 pi r squared. Go ahead and plug that in for area. And we have found the total charge on this hollow half sphere, on the surface of the hollow half sphere. All right, so that's for a non-calculus application there. Let's look at calculus ways of writing these 3 equations. So in calculus, we are very much focused on infinitesimals, or little pieces of the system. And what we try to do is we try to look at an arbitrary piece of a system, and we try to kind of describe what's going on with that infinitesimal piece in a way that would be true for all such infinitesimal pieces that comprise the entire system. Once we know the rules for each little thing, then we can go ahead and integrate across the whole system if we're lucky. And what we end up with is a solution for the whole system. So calculus actually means little stone. So, taking a little chunk of something, evaluating it in a way that's true for all such little chunks, and then from there it's history. Pretty amazing stuff. So these equations, one way I suppose you could think about this is you could say that a little bit of charge, or an infinitesimal amount of charge, could be written as the linear charge density times some little bit of length. So I'm using dl here for a little bit of length. I might on occasions use d little s, so lambda times a small segment of a curve or a circle. So usually I tend to use dl when things are straight, and ds when things are a curve. So dl for small line, ds for small segment. And oftentimes you're just going to have a wire in the x direction. So you could very well write this as lambda dx, or maybe it's a wire in the y direction, lambda dy. But either way, the units work out for all of these. And so these are all valid ways of writing different problems. Now, the other 2 equations don't really have as many ways to write them. So another way we could find a small amount of charge on a surface is we could take the surface charge density and we could times it by a small piece of area, right? Our infinitesimal chunk of area. And there's probably other ways to write this one. In this class, I think dA is going to be the way to do it. And then another way for volume charges, we could find a small bit of charge, or an infinitesimal amount of charge, by taking the volume charge density and timesing that by a infinitesimal bit of volume. All right, so these 3 equations, particularly, well, I suppose these 2 are actually the only ones we're really going to see in action in this next section. So that's what my next video will be about. It's about finding the electric field caused by a charged surface or a charged wire at some distance, at some orientation. All right. Well, I hope this was beneficial, and I hope to see you next video.